Hi guys, welcome back. In this video, we will be talking about how to draw Lewis diagram for atoms and molecules. So first, let's do a little review about the periodic table. So as we know that the columns are called groups or family, and the rows are called period. And the group number or the family number tells us the number of valence shell electrons in a particular atom, and the period number tells us the number of energy levels in a particular atom. So using this knowledge, we can draw the Lewis diagram for atom, and a Lewis diagram can efficiently tell us how many valence shell electrons are there. So let's take a look at a few different examples. So the first one, let's take a look at aluminum. So as we know in the periodic table that aluminum has a atomic number of 13 and it is in group 13, which means it has a valence shell electrons, three valence shell electrons. So we can draw these three valence shell electrons like this. So we start from the top and we go clockwise. So we can go like this. First valence shell electron, second electron, and third electron. So this can tell us that, oh, aluminum has three valence shell electrons. The second atom that we are going to look at is sodium. And we know that sodium is from group 1 right here, which means it will have only one valence shell electron. So we still go from start from the top, and boom, that's it. We can clearly tell that sodium has only one valence shell electron. And the next atom is iodine. So iodine locates right here, and it's in group 17. It is a halogen element. And if it's in group 17, which means it has 7 valence shell electrons. So we still start from the top. We go 1, 2, 3, 4. And the fifth electron will be grouped together or paired up with the first electron on the top right here. So 5, 6, 7. So we always work clockwise, And as we see for these three examples, that in a Lewis diagram for an atom, there are always 4 orbitals, which has the capacity of containing 2 electrons as its maximum. And for the first round, we're trying to put 1 electron in each of the orbitals before pairing up or doubling up the electrons in an orbital. And the next one is neon, which is a noble gas right here. And it's in group 18, which means it will have 8 valence shell electrons. So we start go from the top. 1, 2, 3, 4. So until now, we have successfully put 1 electron in each of the orbital. And then we are going to pair up the electrons in the orbitals respectively. So we continue 5, 6, 7, 8. So this would give us the correct Lewis diagram for neon. And from this Lewis diagram, we should be able to identify 2 important information. The one is called lone pairs, and the second one is called bonding electron. So when we are talking about bonding, either ionic bonding or covalent bonding, we are talking about what kind of electrons are participating in this bonding process. So if some electrons are alone like this, they're called bonding electrons and they will participate in the bonding process. Whereas a filled orbital which has two electrons are called a lone pair, which does not participate in the bonding process. And we're going to see that more clearly in the next section, which where we will talk about how to draw the correct Lewis diagrams for molecules. So let's look at a simple example first. So let's go with hydrogen gas, which is represented by H2. So we can draw the individual atoms first. So we know that hydrogen has only one valence electron because it's in group 1. So the Lewis diagram for hydrogen atom, for one hydrogen atom, will be like this. And we have two of these. So in order to draw a Lewis diagram for molecules, and in this video, we're specifically talking about covalent bonding. And covalent bonding means that atoms are effectively sharing electrons such that they can achieve a more stable state. So when we are drawing these diagrams, we're always trying to follow octet rule, which is essentially saying that the most stable state for an atom is when this atom has 8 electrons in its valence shell. Exception would be hydrogen, where it only needs 2 electrons in its valence shell to achieve its stable states, which is essentially in this case right here, hydrogen gas. So we have 2 hydrogen, each has 1 valence electron. So what if they share these 2 electrons in its valence shell? So this electron comes from this hydrogen and this electron comes from this hydrogen, and they're sharing such that in each hydrogen atom's valence shell, they both have 2 electrons. So they're happy, they're stable. Therefore, this would be the correct Lewis diagram for hydrogen gas molecule. And in Lewis diagram, we use a dash to represent a paired up electron. So we use this to represent hydrogen gas. Next, we're going to look at another example. We're going to look at this, which is hydrobromic acid. So we still are going to draw the individual atoms first, the Lewis diagram for each individual atom. So hydrogen has 1 valence electron, and bromine is a halogen atom which locates in group 17, which means it has 7 electrons in its valence shell. So we're going to draw 1, 2, 3, 4, 5, 6, 7 like this. So we can see that hydrogen has 1 bonding electron, bromine has 1 bonding electron, and these 3 lone pairs do not participate in the bonding process. So we can see that this hydrogen needs 1 more electron to achieve its stable state, and this bromine also needs 1 electron to achieve its stable state because of the octet rule, which means we can let the hydrogen and bromine share the electrons, the bonding electron they have. I'm going to use different colors to represent the electrons originated by each atom. So we can see that if they share these two electrons in each of their orbitals, they're going to achieve their stable states. For hydrogen, it is 2 electrons, and for bromine, it is 8 electrons. So both of them are happy now. And we're going to draw the structural Lewis diagram as H dash bromine because there's a covalent bond of 2 electrons that's being shared in between these two atoms. And we're going to, sometimes we're required to draw the lone pairs as well. And next up, we'll be looking at phosphorus chloride. So this is a little bit more complicated, and we're still going to look at the each individual atom's Lewis diagram first. So phosphorus is in group 15 right here, which means we'll have 5 valence electron, and chlorine is a halogen, and it has 7 valence electron. So we will draw these individual atoms Lewis diagram first. So for phosphorus, we will have 5 valence electron, and for chlorine, we will have 7. 6, 7. So we can see that this phosphorus has 3 bonding electrons, while this chlorine only has 1 bonding electron. And we call the number of bonding electrons an atom has bonding capacity. So when we have more than 2 atoms involved in a molecule's bonding process, we always want to find the central atom first. And the method to find the central atom is to find the atom that has the highest bonding capacity, which means we're trying to find the atoms that has the highest number of bonding electrons. In this case, the phosphorus atom will be our central atom because it has 3 bonding electrons, which is the highest bonding capacity in this case. So we'll put our phosphorus in the middle. And we can see that this chlorine needs 1 more electron to achieve its octet valence electron, which means we can put our chlorine here to share this electron with the phosphorus. And I'm going to use cross to indicate the electrons originated by chlorine. And we can put another chlorine here and another chlorine here. And we can see by doing so, in phosphorus valence shell, it has 8 electrons. In each of the chlorine valence shell, they also have 8 electrons. And they're happy. All of them are happy now. So essentially, there are 3 single pair covalent bonding happening in this molecule. So for structural Lewis diagram, we are going to draw like this. We're going to draw P, a chlorine here, a chlorine here, and a chlorine on the right side. And sometimes we're required to draw the lone pairs that do not participate in this bonding process. And sometimes in the covalent bondings of molecules, it may not necessarily be a single bond, a single pair of electrons. Sometimes it could be double bond or triple bond, and triple bond would be the maximum. And we are going to look at one example of this multi-bonding example, which is very common molecules in our world, carbon dioxide. So, as usual, we're going to first draw the Lewis diagram for each individual atoms. And then we're going to find our central atom. And in this case, we're going to see that carbon has 4 bonding electrons and oxygen has 2 bonding electrons, which means our carbon will be the central atom because it has the highest number of bonding electrons. So we're going to put our carbon here, and we have 2 oxygen. So likely we're going to put our 2 oxygen on both sides because symmetry yields a stable structure. So as we know that we have 4 bonding electrons for carbon, and we have 2 lone pairs that do not participate in this bonding process, and 2 bonding electrons for oxygen that do participate in the bonding process. And same thing happens on the other side. So we have these 2 for oxygen that are actually participating in the bonding process, and these 4 for carbon. So ideally, carbon would need another 4 electrons to achieve the octet rule. And for oxygen, it would need 2 more electrons for each oxygen to achieve 8 electrons in its valence shell. So since for each oxygen it needs 2 more electrons, so we're going to let the carbon generously share 2 electrons with oxygen, another 2 electrons with this oxygen right here. So by doing so, we're going to have something like this. So we have this, and we have they're sharing these electrons. And actually, I'm going to use different symbols. So the crosses are electrons originated by carbon, and they're being shared with the oxygens on both sides. Therefore, in this oxygen's orbital, in this oxygen's valence shell, it has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons as desired. And on this side, it also has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in its valence shell. And for the central carbon, in its valence shell, since it's these 4 electrons in the oxygen atom are being shared with the central carbon atom, the carbon atom will also have 8 electrons in its valence shell as desired. So by doing something like this, we will achieve the octet rule and stable structure for all 3 atoms. And we're going to draw the structural Lewis diagram like this. We're going to use 2 dashes to represent 2 paired electrons in the bonding process, 2 covalent bonds. And you will notice that for each dash, it represents 2 electrons. And that is how we can draw the correct Lewis diagram for both an atom and molecules. Thank you for watching.